So here we have part 1 of B2 of this paper, and we have that it's under oscillations of waves. So here I have my my formula booklet with that section. So a rectangular piece of wood of length L floats in water with its axis vertical as shown in diagram 1. Then it says the length of wood below the surface is D. The wood is pushed vertically downwards at distance A such that the length of the wood is still above the water surface as shown in diagram 2. The wood is then released and oscillates vertically. At the same instant shown in diagram 3, the wood is moving downwards, so it's moving downwards in that direction. And the length of the wood beneath the surface is D plus X. So if I have a look at this, this is when it is stationary. This is our equilibrium line here. And so this piece of wood is going to be oscillating to and fro, that way and that way, a distance A. So in terms of my formula, we're going to get our x0 is equal to A. Okay. Now it says on diagram 3, draw an arrow to show the direction of the acceleration of the wood. Now it's not given in our data booklet, but our key formula here is that A is equal to minus omega squared x. This is the angular frequency. Your acceleration is proportional to your x. It's always in the opposite direction to the direction of that x. So if it's going this way, then your acceleration must be in that direction, in the opposite direction. Then it says the acceleration A of the wood in meters per second is related to x by the following formula. This formula over here. Explain why this equation shows that the wood is executing simple harmonic motion. Well, it's because A is proportional to x, as we can see there. This 14 over L is a constant, so we have A is equal to kx, so it's proportional to x, and A is in the opposite direction. To the x, because you can see here we have this negative sign that is shown by the negative x, Okay, so because you've got this negative sign over here, it shows that your A is always in the other direction and it's proportional to x. Okay, good. Let's go on to the next part of the question here. It says the period of oscillation of the wood is 1.4 seconds. Show that the length L of the wood is 0.7 meters. Now we had there our formula that was given. The formula over here was A is equal to minus 14 over Lx. So we're going to need that. A is equal to minus 14 over Lx. Now, we also have that A is equal to minus omega squared x. So omega squared must equal to be 14 over L, or L is equal to 14 over omega squared. Now from this formula over here, we see that omega is equal to 2 pi over t. Now we are told what our period is. It's 1.4 seconds. So we can work out our omega. Omega is equal to 2 pi over 1.4. And therefore omega squared is equal to that, all squared. So L is going to equal 14 divided by 2 pi over 1.4 all squared. And when we do that, when we calculate that, we get to about 0.7 meters. 0.70 meters. L is about 0.70 meters. So see if you get that when you do that calculation. Next it says the wooden A, as shown in diagram 2, is released at time t is equal to 0. So now in diagram 2, let's just go back to that diagram. Sorry, we just got to go to and fro here. So we're in diagram 2. So we are releasing it at this position over here. So we're releasing it when your x is equal to x0. We're releasing it at that point. So when we do that, we actually use these formulas over here, where your x is actually at a maximum, and that's why your start is a cos theta, because we know our cos graph starts there and it goes like that. So your x is going to be a cos graph, and with x0 at your starting point, in that case that would be a that you'd be starting off with. Alright, so knowing that, let's go back to our question and let's think of it a little bit more. So we go back here. Is released on the axis below. Sketch your graph to show how the velocity v of the wood varies with time over one period. Now as we said, it's this one over here. Now this over here is the velocity graph. Now I'm just going to draw in for a moment. I'm just going to draw in our x1 just to talk about this for a moment. So we've got, this would be our x. Now we know that the velocity from a displacement time graph is a slope. So we can see here that our slope starts off at 0 and it starts to go down like that. And that's why we have a negative sine graph. So when I draw my v, I'm actually going to have this graph over here. It's going to be the negative sine graph. So if I just put in my points like this, to be something like this, would have, this needs to look like a sine graph, where this would be minus v0 and that would be v0 over there. So that would be your graph that you would draw. Then it says calculate the magnitude of the maximum acceleration of the wood. Now we know that acceleration is equal to minus omega squared x, and we know that this over here is 0.12. We already have worked out for this one, we can use this, but we could also use our a is equal to minus 14 over 0.7. Remember, we work that out as the length, times our maximum distance, 0.12, because you're going to get a maximum acceleration when you're actually at x0, your maximum displacement or your amplitude. So when we put that all in, we get 2.4 meters per second to the minus 2. We don't actually have to worry about the negative sign, because that obviously changes, because we were asked to find just the magnitude, so we're looking just for that value there. And then on your sketch graph, in B, label with a letter P one point where the magnitude of the acceleration is a maximum. Now that's wherever you're going to get your velocity is 0, because that occurs when you are at your furthest points from your equilibrium. So you could label any one of these points over here. That would work. If I just go back to my graph here, you see this is oscillating to and fro this way. So it will go, it oscillates between these 2 points. Your equilibrium goes a distance a that way and that way. Now when you're at your equilibrium, your velocity is a maximum, but your acceleration is 0. But when you're at over here, your velocity is 0, but your acceleration is a max. And the same over here, when it goes up there, when your equilibrium position is over here, your velocity is equal to 0, your acceleration is a maximum. Okay, I hope that is reasonably clear. So going down here, and now moving to this part of the question, which is looks at this. It says the oscillations of wood generate waves in water of wavelength 0.45 meters. The graph shows how the displacement d of the water surface at a particular distance from the wood varies with time. So this is showing a specific point on the surface of the water as it goes up and down with time. So using the graph, calculate the speed of the wave. Now we have our general formula for waves, that v is equal to frequency times wavelength. Now we are given the wavelength here, so we have that already, but from our graph we can actually calculate our frequency, because we know that this over here, at that point over there, we have gone one full oscillation. So that time period is your period, is equal to 1.4 seconds. So your frequency is equal to 1 over t is equal to 1 over 1.4. So we can put it into our formula. The velocity is equal to 1 over 1.4 times by 0.45, and that will give us our speed of our wave. And it works out to be 0.32 meters per second to the minus 1. Okay, then looking at this one, it says the ratio of the displacements at 1.75 seconds and 0.35. So 1.75 is, I just take this all away, 1.75 is over there, so I'm over there, and 0.35, we probably are over here, are we not? So we're over there and there. So in looking at that, I'm about here. 3.7 is at 0.35, and here we are at 2.8. So it's going to be 2.8 over 3.7, and we're looking at that ratio. We're looking at 0.76. Okay. Now, the last question here relating to this is the ratio of the energy of the wave. Now, if we look here, we see that the energy here of the wave is related to a x squared. For both of these waves, we're going to have our omega the same, the mass is the same, but our energy is related to an x0 value. So therefore, the displacement, when we're looking at energy, we would have to square that term. So if this was if the ratio was between the displacements was 0.7, for the energy it's going to be 0.76 squared. So if this ratio was 0.76 for that displacement, then it's going to be that, and we're going to get about 0.57 will be the ratio of the energies.